I'm told there's a graphene conference this week, somewhere in the world, in Germany, so maybe some graphene people are gone. This is a little bit of a difficulty. Cuprate superconductors, we could talk about them for the next 10 lectures. So this is just a selection of some facts, and we'll see how far we get. I think we should probably try to go slowly and think about things. So last time, Ivan, who's unfortunately not here, asked a question about, could I explain something about, oh, and here he is. Could I explain something about the hexitonic mechanism of superconductivity? So just as I did in lecture 3, I talked about an update on applications from lecture 2. Today, before I start the lecture on cuprates, I'm going to talk about the hexitonic mechanism of superconductivity. And as you'll see in these lectures, we can spend all of our time going into details in particular directions. So the definition, and we'll see a picture and you'll get this a little more understood. An exciton is a bound electron-hole pair. And for that to happen, you can't really have a metal. You have to be something where there's not good connectivity, or these electron-hole pairs would recombine and you wouldn't have an electron-hole pair, but they're bound to each other. And we'll see a picture of that. So there's a lot of theory running around. The start of this, somewhat earlier than this, but this is a more recent discussion, is from Ginsburg. Bill Little was the guy at Stanford when I was a grad student who was pushing superconductivity in sort of one dimension. And I had the good fortune to go to a physics lecture when I was a grad student, and Bernd Matthias, the godfather of superconductivity, was giving the lecture. And Little came a little late, and he sat down right in front of me, and he had a paper bag. So, okay, professors walk around with paper bags, okay. So during the lecture, Matthias got to the point where he started talking about superconducting transition temperature as a function of dimensionality. And of course, Bill Little was one dimension, right? So as soon as he started that slide, Little opened up his paper bag and took out a construction worker's hard hat and put it on. And we all had a good laugh. And so Matthias said, TC in one dimension, 0. TC in 2 dimensions, the layered dichalcogenites, which we talked about, goes up. TC in 3 dimensions goes up some more. He says, since we're talking about transition temperature as a function of dimensionality, let's talk about the 4th dimension. And then he looks at Little, because he thought superconductivity in 1 dimension was unrealistic. So if that was unrealistic, he said, well, let's talk about the 4th dimension. And he said, well, if you look at this plot, you know, from 2 to 3 dimensions it goes up, so it doesn't look like it's going to go down. It doesn't look like it's going to stay the same. So I make the prediction that in 4 dimensions, TC goes up. And then he looks at Little some more. So we all had a good laugh. But Little was a theorist. And if you go read this article, which I think is open access, or you certainly have access to it through your NUS account, it's like fiction. I mean, it really is full of stuff that's fictional, but it's entertaining at least. And here's a somewhat more scientific discussion. So anyway, let's get on to how this works. So instead of an electron causing a disturbance in a lattice, like we've seen, and moving the lattice ions around and leaving a retarded attractive interaction to a second electron that comes by, instead of that procedure, instead of just causing a disturbance in a lattice of ions, what Little is talking about is creating a similar idea, only now he's got side chain molecules. So let me just show you this picture. here is something that Little calls the spine. It's a bunch of carbon bonds going up the one-dimensional pathway, if you will. So in Little's picture, an electron comes, just like we saw in the BCS three-dimensional lattice picture. In Little's picture, an electron comes up this one-dimensional pathway. And as the electron comes up, and this is impossible to see, but it's the best copy I can get, as the electron comes up, it repels an electron on a nitrogen off to a further location, and so it leaves behind a hole. And so this combined hole and moved electron, and you can't even see the minus sign in this plot, but this combined hole and electron is what is called an exciton, and there's one on this side. And so as the electron goes by, it causes, on these side chain molecules, an electron to move around and to have a positive ion closer to the spine. And so when a second electron would come along, it would see this effective interaction. And as Cooper proved, way back in the BCS theory, even if the net attractive interaction is as small as you can make it, as long as there's a net effective, positive, attractive interaction, you'll get condensation into a superconducting state. So Little's idea was the electron going up the chain polarizes the side chain molecules. And of course, if you think about the chemistry, I mean, the possibilities for looking at side chain molecules on things, I mean, it includes DNA. So there's just a whole smorgasbord of possibilities here. And so the moving electron polarizes each side chain molecule, inducing a positive charge near to the spine, balanced by that shifted negative charge further away. And so that's the excitonic mechanism, that's the idea. And where the numerology, or where the size of TC comes in, since the object causing the polarization is no longer some heavy lattice ion, but it's just an electron, then this 1 over square root of mass is enormous. So that was Little's point. He's polarizing excitons. He's got a whole electron excitonic pair, and making a much higher characteristic temperature. This sort of picture is what's going on these days in the 200 Kelvin superconductivity in hydrogen sulfide, where the idea is that the hydrogen is what's causing the superconductivity, and so 1 over the square root of the mass of a proton for hydrogen is a much smaller number than 1 over the square root of the mass of a lead ion. But if you're talking about excitons, then that number gets even larger. So Little had this idea. There was later a one-dimensional superconductor, sort of embarrassing to Matthias, called polysulfur nitride. TC is around a Kelvin, so it's not high temperature. So rather than polarizing organic molecules, which isn't really something you can do in a complete fashion, now I've done it and now we see what the answer is, following the theory of the Alan de Bray and Bardeen theory that I mentioned in an earlier slide, people started trying to take a superconductor on a semiconductor substrate and tried to see if they could get an excitonic mechanism occurring in the semiconductor substrate. And so if you read this paper, which is a little theoretical and fairly long, you can see that one of their indicators if the excitonic mechanism is actually working is the thickness of the superconductor. The TC as a function of the thickness of the superconductor will have a maximum at some rather thin, small multiple of a lattice atomic spacing. And this was not seen. And more or less, they didn't see an excitonic enhancement of superconductivity in anything they looked at. They saw a lot of decreases. And Phillips came along and said, well, you silly people, When you have an interface between the superconductor and the semiconductor, you're going to get some interface states, and these interface states are going to prevent you from having your hexitonic mechanism give you an enhancement of superconductivity that's at all substantial. And so this hexitonic mechanism more or less died in terms of practical possibilities. If, however, you are in possession of a superconductor that you can put on a semiconductor or an insulator where there aren't any localized interface states, you too could revisit this. So again, do I have any undergrads coming back? Yes, there we go, excellent. Get rid of the interface states. It's possible. They don't have to be there. So now we're leaping back into the main theme of the talk, which is the Cuprates. I've shown this slide before. We've told a little story. I will now tell the Carl Alex Mueller story. I have to slow this down a little bit, or we'll get through all the material too quickly. Frank Steglich, who was a director at the Max Planck Institute in Dresden at the time, had his 60th birthday and invited a bunch of famous people, one of whom was Carl Alex Mueller. Carl Alex Mueller is a very non-pretentious guy, right? He drives a nice car, a Jaguar, but it's an old Jaguar. You know, it's almost a classic. He brings his wife with him, which I do when I go to conferences. You know, he sits at table and he converses with everyone. He's not stuck up or arrogant. He's very, very collegial. And so the women, you know, Professor Steglich's wife and my wife and Alex Mueller's wife and a few others, Bertram Batlogg brought his wife, they would sort of go together and do things while the rest of us were having scientific discussions to celebrate Steglich's birthday. And so Mrs. Mueller needed some toothpaste. And so Professor Mueller, since they traveled from country to country in the Jaguar, had an envelope of foreign currency in the glove compartment. And so they weren't in Switzerland, now they were in Germany, where the euro was in force, or maybe it was the Deutschmark. It was in 2002, a little big, but anyway. So she reached in the envelope and got what her husband had provided her for local money. And I guess it was D-Mark. It was 1,000 D-Mark note. And so she tried to go into the local apothecary and buy some toothpaste with 1,000 Deutschmark note, which was of course impossible because they did not consider themselves a bank willing to change the 1,000 Deutschmark note. So the wife of Professor Steglich leaped in and paid for it. So that's my Carl Alex Mueller story for the day. So you've seen this already. TC makes this big jump thanks to their discovery. And as we'll talk about probably next time, this was not, to go from here to here was not a difficult thought process. And now we could spend the rest of the year on this question. If they are unconventional, which it is certain that they are not BCS mechanism, with one exception. If they are unconventional superconductors, what is the pairing mechanism? And of course the theorists leaped on this immediately because the theorists knew that there was a recognition, fame, fortune, and maybe even a Nobel Prize if you could figure the answer out. Unfortunately, as we'll see, the properties of cuprates are sufficiently numerous and inconsistent within themselves that it's hard to understand on a global picture all of the properties of the cuprates, like Bardeen, Cooper, and Schrieffer managed to do for the elemental superconductors and for the lower TC compounds. BCS theory explained lots of things. It explained the isotope effect, it explained the energy gap, it explained the penetration depth, it explained the coherence thing. BCS theory explained a lot of things, as we talked about in lecture 1. And such an overriding explanation for the cuprates does not yet exist, and since you're filming this, when you publish this on public media, there are at least 3 theorists who will put out a hit contract on me and wish me dead, because each of those 3 theorists, separately from the other 2, believe that they have the explanation for ITC superconductivity and that they're correct. So do not go to a meeting with these 3 theorists, and I won't name their names because I'll get in even more trouble, and say there is no overriding theory for superconductivity, because each of these 3 theorists believes, personally, that their theory is correct. No comment. Okay, so instead of the BCS glue, which we talked about, what's the answer? Do I look like a theorist? No. However, one of the front runners for the explanation is that it's some sort of magnetic interaction. Hexitonic has been ruled out for various reasons, but the idea is that you have these spins. This would be strontium ruthenate, and the spins can orient in various directions. And if they exchange spin fluctuations, which is meant to be this wiggly green line, you can get a pairing of these spins rather than an S = 0 BCS oppositely aligned spin orientation. You can get a P wave L = 1 spin aligned state, which is believed to be the answer for strontium ruthenate. So there are lots of indications that magnetism and ITC cuprate superconductivity are intimately intertwined. So this is probably a good guess. You can read an argument between Scalapino and Phil Anderson. Let's see, excuse me, between Doug Scalapino and Phil Anderson. Scalapino likes the exchange of spin fluctuations, and Anderson points out that they need to be ferromagnetic spin fluctuations. And as we saw in the first lecture, and as we'll see again, all of these things are anti-ferromagnets. So Anderson points out that the frequency involved in exchange of anti-ferromagnetic spin fluctuations is too high to explain a bonding mechanism. And then Scalapino wrote back in a further paper explaining why Anderson was wrong, and that's the point at which I stopped understanding the argument. But you guys can go find it and read it for yourselves. So I don't claim to know what the answer is. It's not electron-phonon interaction, except for lanthanum copper oxide. The very first one that was discovered has a positive isotope effect and looks to be BCS-like. At the time when we were talking about 30 or 35 Kelvin for that material, people said, well, that's awfully high. The other record was 23, but now we have magnesium diboride, which has a TC of 40, and that's known to be BCS, electron-phonon exchange pairing. So now 35 for the lanthanum copper oxide doesn't seem so high. So that's a known fact. Now, if you want to explain something, one of the ways that people who like to collect facts, which would be, including others, myself, one of the ways that people who collect facts like to do it is, let's see if I can find a correlation between the superconducting transition temperature and some other physical measurement. If I find a correlation, then I can say, well, look, there's a correlation. That other physical property that I'm measuring must somehow be involved. And then you can start thinking. And that's a very profitable way to do things. In this particular instance, this is Moria and Ueda. And what they pointed out is if you take a relatively commonly accepted measurement, I danced around that. Everyone noticed I danced around that for the undergrads. Relatively commonly accepted. I didn't say everyone accepted. Relatively commonly accepted measure of the spin fluctuations, which I have been known to do. In my latest paper, I used it for a compound that it couldn't possibly apply to, and the referee caught me, so I took it back out again. You do have to be careful. If you're talking about spin fluctuations as the cause of your superconductivity, you better not be talking about it in a system that has a known BCS isotope effect. So don't go explaining your data based on exchange of spin fluctuations if it's known that it's a BCS isotope material, which is what the referee caught me at, although he was polite and gentle and wasn't too brutal in saying, I don't really know. So anyway, what you do is you take the electrical resistivity and you plot it versus temperature, and if it has a linear term, which is very often the case in many materials and certainly in the cuprates, the linear term in the cuprates goes up to 500 or 600 Kelvin. It's some huge temperature range. So you take the slope and you calculate this characteristic T0 here, and you plot it versus TC, and you find out that it lies on a straight line. Now, for those undergrads who need to be skeptical in your future careers, please notice that the vertical axis is a log plot. So when you see deviations from the straight line, like uranium platinum 3 is way down here and this line is way up here. If this were a linear plot, you'd say, oh, Professor Stewart, 20, 30, 40%, so what? It's a log plot, or a semi-log, well, actually a log-log, excuse me. So this is a serious deviation. This means that sticking this into the theory, you've had to put a lot of pressure on it to get it to fit. Whereas you see the cuprates look pretty good. Okay? So one of the methods for figuring out superconductivity is to look at a correlation. Now, dimensionality is, of course, very important in the cuprates. We looked at the transition metal dicalcogenides and saw a ratio between conductivities in the plane and perpendicular to the plane of something like 1,000. That's also true in things like BISCO, and we'll look at the structure. So these are not A15 cubic 23 Kelvin superconductors or 18 Kelvin diameter 310 superconductors. These are layered structures. And we could also spend all day on this. So the first material that was discovered to be a cuprate superconductor by Bednorz and Müller had barium doped on the lanthanum site. This is, and we'll talk a little bit more about this, this is an anti-ferromagnetic insulator or semiconductor, depending on how you want to define, but it's got a band gap of a couple of eV. So this is not anything like a metal, but if you dope some holes on it, you can get it to be superconducting, which is what Bednorz and Müller discovered. So if you look at the parent compound, if you grew up around Matthias, you learned some of his wording, which when you hear it in the community today, you know that this person was in Matthias's orbit for a while. He used to call that the mother compound. Now these days, of course, we all have to be politically correct, and somehow that would be not gender neutral, so you'd have to sometimes call it the father compound. Well, no, the parent compound. We get away with that. But Matthias always called it the mother compound. So the copper is what's carrying the magnetic spin. You don't normally think of copper as magnetic, but it's got some nice 3D electrons. And the spins are oriented in the fashion shown. And there are planes of copper-oxygen, and the symmetry here is a copper O6 octahedron. So here's your copper oxide layer, and the connectivity in this direction is something like 1,000 times the connectivity in the C-axis direction. So it's an anti-ferromagnetic insulator, if you want to say that 2eV is an insulator, not a semiconductor. And it has a Néel temperature of 240 Kelvin. That's very important to remember, and we'll see it in a diagram soon. all the cuprates have those copper oxide layers. But in addition, YBCO has copper oxide chains, but that's unique. So when you're thinking about how to explain all of the cuprate superconductors together, don't go running off down the road and saying, it's the chains, it's the chains. No, it's the planes, and maybe for YBCO plus the chains. But anyway, so in the picture you can see where the copper oxide chains occur in YBCO. So in lecture 1 I gave you this because I was being gentle. In lecture 4 I give you the whole Monty here. So it's the discovery compound, the next discovery compound, and then bismuth, thallium, and mercury-based compounds. And here is a short list, not complete. So rather than that little brief blurb that I gave you in lecture 1, this is what you need to see. And Phil Anderson was the one that noticed, although I'm not sure he's unique, he's certainly the one that gets the credit, that as you added layers, there was a peak at n equals 3. So if you take the bismuth family, and you take the number of layers, you see that at 3 there's a peak in TC and then it goes back down. If you take the thallium family, and you look at the TC, you see there's a peak at 3 layers and then it goes back down, and etc. Okay? So, when you're doing your overarching theory of the cuprates, and you're deciding between chains and planes, don't forget the layers. Because just like BCS, your theory has to explain that. You can't say, oh, well, I'll leave that for later. You're not going to get the Nobel if you say, oh, well, I'll leave the fact that n equal 4 has a lower TC than n equal 3 in all the families. It's a fact, and it must be important. No one understands. That's why the Nobel hasn't been given yet. Okay. And this is a bit of a quibble and doesn't make a whole lot of difference. Tetragonal means that the A and B axes have the same length and the C axis is different. It could be either larger or smaller than AB. YBCO is orthorhombic, which still has right angles between the axes, but it just means that A is not equal to B, is not equal to C. But the difference is not that big. So that's a somewhat of a qualitative difference. Okay? So we talked about that. And how do we get superconductivity? You know, we say strontium these days, but remember the original material in the same column in the periodic table was barium. Doesn't really matter. It makes a little cleaner, more single-phase sample. And if you look at who gets credit for what, and we'll talk about that more next time, Bednorz and Mueller discovered that this sort of structure had a great potential for high-temperature superconductivity. That got recognized, even though their original article was published in Zeitschrift für Physik B, not exactly your high-impact journal. And people have said, well, they were trying to hide it. No, they weren't. They sent preprints to everybody. They weren't trying to hide it. It's just they were German-speaking, and for German-speaking people at IBM Zurich, they used Zeitschrift für Physik B. Steglitz later became an editor for Zeitschrift für Physik B and tried to convince all his colleagues, including moi, that we should submit to Zeitschrift für Physik because that was the up-and-coming journal. No one listened to him, and its impact factor is what it always was. Except for this one article. So the article that came after their article that actually solved the structure, I mean, we showed you the structure, Bednorz and Mueller didn't really know. They were shaking and baking. They were mixing ceramic powders. They sort of had a general idea about the structure, but they hadn't really solved things. It was Bob Kava at Princeton who did the solution, and his solution of the structure has a lot of sites. Not as many as Bednorz and Mueller, but it's a very well-known paper. Probably talk about that next time. Okay, so I will tell you the truth. When I'm looking for phase diagrams for the cuprates, I'm lazy. And I also like the latest one. So the latest one is in a review article on the electron-doped cuprates, which are sort of boring because their TCs are in the 20s and not in the 90s. But there's a lot of physics hidden in there. And this latest phase diagram comes from Rick Green and co-workers who wrote a review on the electron-doped cuprates. And I won't spend a lot of time on those, but it's like lanthanum copper oxide, lanthanum 2, copper 1, oxygen 4, 214, but instead they stick some cerium in, and in fact, in place of lanthanum, they also can put praseodymium. So there's something called PCCO, praseodymium cerium copper oxide. And the TCs, as I said, are down here around 30, and there's all these graphs. So you see that the parent compound, depending on what the parent compound is, in other words, remember on the left we're starting off with lanthanum strontium, sort of the Bob Cava, Bednorz-Mueller original, and on the right we're talking about something else. So this is not necessarily lanthanum, this is some rare earth. So when we have x equals 0, when we have no cerium, this still doesn't have to be the same, and obviously on the picture it's not. But you have an anti-ferromagnetic transition in this insulator, semiconductor, whatever you want to call it, 2eV band gap. And then as you dope over here, you dope with strontium, over here you dope with cerium. As you dope, the anti-ferromagnetic transition gets suppressed quickly or slowly, depending on what you're doping with, which side you're on. Then you have some complications. Now this slide is hiding it from you, but there's complications hidden in there. But here there's spin glass, and Carl Alex Mueller spent a lot of time theorizing, even though he's an experimentalist, theorizing about the effect of the spin glass. And again, if you want to talk about exchange of magnetic excitations in the superconducting dome, you're hard put to talk about coexistent magnetism, because the coexistent magnetism doesn't coexist because the magnetism dies way over here. So if you want to talk about any sort of magnetism that's present, you're stuck with doing the spin glass. Whereas over here, you can have the antiferromagnetic transition temperature get depressed and wind up running into the superconducting dome. So here, having coexistent magnetism and superconductivity, just like in the iron-based superconductors, is easy and present. And you know, for someone that's not in the field, this is a very busy diagram. Here is this T star, which we're going to talk about today. We're going to spend a lot of time talking about T star. Here is some other characteristic temperature in the phase diagram, which is not an if. It is a real, honest-to-God, well-known experimental fact characterized by many different measurement techniques. And what it does is it points out where the pseudo gap starts. So down here at superconductivity, a full gap opens up in the electronic spectrum. There are no electronic states between 0 and 2 delta, where delta or 2 delta over HEC might be something like 3.5. So understand that if you're talking about a 100 Kelvin superconductor and you say that delta is something like 1.76, that's the BCS number, so it's not the case. But let's say, you know, it's 1.5 times the TC. TC is 100. 1.5 times that's you know, it's 150. So the energy gap is quite large. But in addition, there is above the temperature where the superconductivity opens up that full energy gap, there is something called a pseudo gap, which is nothing more nor less than a partial gap. There's nothing pseudo about it. It's a partial gap, but it's called a pseudo gap. And we'll talk about that. And it is one of the things that your overarching theorist had better explain, and no one can. Okay, here's another phase diagram I just wanted to point out to you, this is on the whole side, so this is reversed from the last picture. And this could be strontium at 214. And there is something happening with TC in here that is something I could talk about if someone wanted to ask me a question, but it's beyond the scope of these lectures. I had a question from someone the other lecture about the scope of the lectures. We're going through a lot of material. There's things that I'm brushing over, but you should at least know that at a particular concentration, TC falls down to immeasurably small. So you can say, oh gosh, it's really fortunate that Bednorz and Mueller missed that particular composition. No, it's not. They were doing shaking and baking. They had compositions all over the map. Okay, they didn't have one single composition. Bob Cava, he had one single composition. But Bednorz and Mueller were a few percent here, a few percent there. Very broad transition. Okay, so each one of these bullets is an entire talk. So for those of you who have a particular favorite, feel free to send me questions and maybe I'll spend more time, maybe next time, explaining your question. So pretty much, except the lanthanum 214, they have D-wave pairing symmetry. Not S-wave, not BCS, D-wave. And the experimental proofs of that, which we'll see one of, are really amazing. Really amazing tour de forces of experimental expertise. And I say this in all modesty. One of the guys that did it used to be my undergraduate thesis advisor when I was an undergrad, C.C. Tsui. So it's nice to know people who went on to be successful. He wanted me to be his grad student in Caltech, and I said, no, I think I'll go somewhere else. Which was good, because after a year he left and went to IBM. Would have been a bummer. So we'll talk about the next one. If you do inelastic neutron scattering, you find a magnetic resonance. Oh, there's that word magnetic again. Below TC. This neutron spin resonance is just thought to be indicative of a triplet excited state of the ground state singlet Cooper pair. The energy of this resonance peak scales with the superconducting transition temperature, implying, now this is a rather weak word, many people would say indicating 100%, we're being cautious here, implying that the resonance is intimately tied to the superconductivity. Okay, the existence of a pseudo gap, as measured by lots of things, and we'll go through that, is a partial opening of a gap, not a full opening, a partial opening. So rather than getting all of the density of states at the Fermi energy gone, some of it goes away, and we'll see that. Is mostly not observed in other unconventional superconductors. I happen to have written a review. Feel free to go out and run my citation index up. I need it. There are one or two other cases where people have claimed pseudo-gap behavior, but none of them are terribly convincing. Okay. Evidence for D-wave pairing. So here's C.C. Tsui, my old boss, and Kirtley, using Josephson tunneling, which we talked about in lecture 1, showing D-wave pairing. Prepare to be amazed. Okay, so what they did was they made superconducting rings out of YBCO, which they think is a D-wave pairing X squared minus Y squared symmetry, they think. So they made superconducting rings out of YBCO, and here's the dimension if you want to know what scale this is. And they put it down on strontium titanate, but on a special substrate of strontium titanate. They aligned the crystals. They found a place where 3 crystals in the strontium titanate came together with this sort of mismatch in the direction of the axes, so that they could have crossing from one crystal to the other, so that they could have an interruption in the phase of the Josephson pair, the Cooper pair. And I'm allowed to say Cooper pair. Cooper pairing does not just mean electron-photon coupling. Cooper pair means paired electrons in the superconducting state due to whatever mechanism. That's a fairly common misperception. When you say Cooper pair, it's due to some pairing mechanism. It's not just BCS. The fact that he was a co-author on the BCS theory is something else. His Cooper pairing came earlier. And there's a control ring down here that doesn't have any crossing of barriers here for the orientation of the strontium tightening. So you've got, so you've got a weak link where the superconducting phase comes here and sees another orientation across this boundary. So there's a weak link here and a weak link here. Similarly, for this weak ring, there are 2 weak links. However, for this one, there are 3. And so, what you need is you need to go around the ring and get a shift of a multiple of 2 pi. For this one, can't do it. Okay? So, such a ring is frustrated, that's their word, and generates half of a flux quantum. And you say, well, that's a nice theory. How about an experiment? So here you go. Here is high-resolution scanning squid microscopy image of those rings, just in the same geometry that we had in the previous picture. This is not the original discovery paper. That was in the 91 or something. This is a review paper where the pictures are prettier. And here you see an evidence of this half of a flux quantum sticking out, measured by the squid. So it's a picture. When somebody that comes from Seamus Davis's group, who does scanning tunneling microscopy on the surface, goes and applies for a job, they have this great advantage because they have pictures that look like this. So when Harry Minoran went to work at Stanford, he was showing, scanning tunneling microscopy pictures of various magnetic atoms on the surface. And Bob Laughlin, who was on the faculty at Stanford in the physics department at the time, is quoted as saying, "How could we not hire him? He has such pretty pictures." Okay, so they have an advantage. So for those of you who are plotting your data, remember to use lots of color. Pretty pictures are good. Okay, so in that list of properties of cuprates, we talked about the neutron spin resonance peak. And obviously, I'm stealing this out of the review from Rick Green and co-workers. Armitage, I think, is the first author, where they're looking at praseodymium, lanthanum, cerium, copper oxide as in electron dope, and then there's a bunch of hole doped data on the plot for higher TC, and obviously the electron dope is lower TC. And this resonance in the inelastic neutron scattering has some energy which is easy to tell from the data, and again, it's just like plotting the linear coefficient of the resistivity like Maria and Ueda did, and seeing a correlation between T naught and TC. What these people are doing is they're plotting the resonance energy from the inelastic neutron scattering as a function of TC, and showing you that there is in fact a correlation. And the undergrads are paying close attention. This is a linear plot. Okay, so where the disagreement comes from is these guys think 5.8 and these guys think 5.3. Okay, so 10% probably not an important thing. Okay, so you might think to yourself, what does this resonance mean? Well, if you go look at the particular wave vector in 214 where the copper d electron spins line up. If you go look at this wave vector in reciprocal space, which is where you find scattering from the antiferromagnetic ordering in 214, the scattering increases dramatically right when you get to TC. Why would that be? Well, just remember, your overarching theory has to explain that. I'm seeing some nods. Can you explain that? No. No. Because I haven't read your paper if you can. Would be very exciting. So, obviously there's a link between the copper magnetic spins and the superconducting transition temperature. Exciting. So here is the idea that the pairing mechanism must be associated with some pairing boson, and it's magnetic instead of phononic. This isn't new information. This is, this is what the data imply. And they're just linking the fact that the energy of the resonance scales with TC like we saw in the previous. Anyway, yeah. But it doesn't help us explain things. It just says there's a connection. I promised you to talk about the pseudo gap. This is now, again, on the other side of the diagram from the first one I showed you. This is now hole doping. There is actually still a big argument in the literature, which when I wrote my review on unconventional superconductivity and advances in physics, which came out just actually a year ago, it's not solved. Depending on which measurement technique you measure the pseudo gap temperature with, it either comes down and goes here, or it comes down and goes over here. And you notice this drawing is sort of wishy-washy. It's not quite to the peak, and it's not quite over here. It's sort of trying to avoid the argument. And everybody on both sides of the argument is sure they're right, and is sure the other guys have misinterpreted their data. I will not enter into this argument. I do not care. Anyway. So it's nothing special. Pseudo sounds somehow highfalutin. It's just a partial gap, and we'll see that. It's just not all of the electrons move away from the Fermi energy, but some do. It's a partial gap. And they manifest themselves differently, particularly in their temperature dependence and their composition dependence, like we just discussed. To give credit where credit is due, and I'm not going to show this slide first because it's a little less clear, but I will show the data. The NMR data were the first to show evidence of this partial gap, and the person that wrote the paper was particularly good with the English language. He said, well, this is occurring above TC. Maybe it's a precursor for superconductivity. And that word has stuck. So you can't talk about a pseudo gap without saying it's a precursor of superconductivity. So it's a highly cited paper. The people that wrote it more or less didn't have a follow-up paper. In other words, Sui and Kirtley turned out a lot of things. Every time a new Cuprate superconductor comes up, Sui and some new collaborator, Kirtley's long gone, Sui and some new collaborator go do their making rings and frustrating the rings and doing the squid scanning of the magnetic field at the surface and publishing in some high-impact journal for the new Cuprate superconductor. Because now, to them, it's a done deal. They just, they got the strontium titanate, they put the superconducting rings on top, they do the measurement, they publish. It's easy for them. So they were not a one-trick pony. They could keep doing this. It's the same kind of trick, but it's a different material every time. But the NMR guys sort of did that one, and that was it, at least in my understanding. Although that's not to say that they didn't do great measurements on other materials. It's just this big splash where they really started the field. This was their contribution. Angular resolved photoemission spectroscopy We'll see pictures of that, etc., etc. Okay. Anybody who's not convinced by this probably should have left earlier. So this is Kyle Shin and Seamus Davis. This is again sort of like Harry Minoran interviewing at Stanford. You know, if you have such great pictures, how can you not get a job? So the idea here is in this material, this is not the same material, nor is it the same temperature. These are two different publications. This is in some bizarre compound, which has a TC of 13 Kelvin, and these data are taken at 15 Kelvin. So there's a gap opened up along the pi 0 direction, along the antinodal direction. There's a gap opened up, and you see, you know, these colors indicate density of electrons, and blue says there's nothing. So over here, along this direction, you see a lot of electron density. This is a non-pseudo gap answer. This is below TC in this material, right? So this is, I'm not trying to demonstrate pseudo gap over here. I'm trying to demonstrate pseudo gap over here. So along this line, you know, from here to here, there's no density, and from there to there, there's no density. So there's a gap open, a partial gap. It's not a full gap, because there is some density here, but it's a partial gap. So over here, you see there's electron density all over everywhere in the Bria-1 zone, and this is in this material, and I forget the numbers, but what's important is that we're below the transition temperature. Okay, I promise you NMR. Here's NMR. And so what you can think of, so we talked about the pseudo gap. When we looked at the ARPAS data, that's a pseudo gap in the electron channel. Now we're talking about a pseudo gap in the spin channel. So here what you're talking about is below this temperature, which is a little over 100, and remember TC for, actually TC for this composition, I think was down here because all you have to do is change the oxygen content. So TC for this one was down here somewhere, I think. So we're looking at 1 over T1T. So T1 is the spin relaxation rate, and so the spin relaxation rate is getting longer. So 1 over T1 is getting smaller, and that's because there's a gap opened up in the spin channel. Okay, so it's not just the charge channel, it's also the spin channel. The pseudo gap opens things up. Somewhat more easy to see, and then for those of you who are paying close attention, you say to yourself, Professor Stewart, this is resistivity, this is low temperature, where's my superconductivity? This is 4%. This isn't in the dome yet. Okay, this is over on the mod insulator side. But as you, well, let's see, it's not so far back. As you remember from the phase diagram, the pseudo gap exists even when the superconductivity doesn't. And so that's what these data are showing, is if you look at the resistivity in something away from the superconducting dome, you know, here's the linear resistivity coming down, and suddenly at a T star of close to 500 Kelvin, an enormous temperature, which we saw on that phase diagram graph, the density of states that's leading to this linear behavior falls, and you come down here. So if you're looking for pseudo gap in your data, and you see some high temperature behavior, and then suddenly it falls off, that's possibly an indication of pseudo gap. So there have been people who will remain nameless, but are in that review in Advances in Physics, who had a superconductor at some number, had a Kelvin above it, they saw a little twitch in the resistivity, and they say, pseudo gap. It'd be nice if you saw it in another measurement besides a little twitch in the resistivity. But anyway, whatever. Depending on how far this gets spread, I could be very unpopular in a certain laboratory. Okay, so that's the resistivity. Not my favorite measurement. My favorite measurement, as we all know, is specific heat. So you can tune TC with the oxygen concentration in all of these materials, getting Tc and delta C, the jump at the specific heat, getting delta C over Tc large is a lot of work. I mean, you got to get the composition really close to 7 for the oxygen. But what you see here is two measures of the density states at the Fermi energy. Obviously, the specific heat, the electronic specific heat divided by temperature as T goes to 0. That's this extrapolation from the normal state. This number, forgetting that there's superconductivity in the way, you take the normal state data and you extrapolate these data, and this intercept down here, extrapolated at T is equal 0, is proportional to the normal state density of states at the Fermi energy, which you see as you get above Tc, for instance, at the 0.8 composition, you see that the extrapolated C over T at T equals 0 is reduced by 50%. 50%. So the density of states at the Fermi energy is down by 50%. And you see also that the delta C, which is another measure with some complications of the density of states at the Fermi energy, is also much reduced. So as soon as you go away from optimally doped, as soon as you go to underdoped, that's just wording, using oxygen as the measurement handle or knob, as soon as you go to underdope, you get evidence of a pseudo gap. And for those of you who are paying close attention over there in the corner, you might say, Professor Stewart, if I take the normal state C over T extrapolation and I extrapolate it, that looks to me like it went up. Looks like it to me too, but at least delta C went down. So I didn't say this was all necessarily clean, but certainly for these materials here, the extrapolated C over T at T equals 0 is lower, and the delta C over Tc is certainly lower, and so there's an indication that a gap is opening. And the problem with looking at the normal state data way up here is that notice what this is. This is the electronic specific heat. The electronic specific heat expressed as a fraction of the total measured specific heat at 100 Kelvin is like 1%, because the lattice contribution is so enormous, because whatever the lattice theta divi is, the lattice contribution goes as T cubed and T fifth, the electronic contribution goes as T cubed and T fifth certainly went over T by the time you get to 100. So less than 2%, more like 1 point something percent, is this as a fraction of the total specific heat. So there's a lot of uncertainty, a lot of scatter in those data. Not sure I could explain that though. Okay, so there's a whole other world out there. So we wanted to learn about what the pairing mechanism was. Well, it turns out that if you do measurements that tell you about time reversal symmetry, or its breaking, you can show that the Cooper pairs have non-zero magnetic moments. Well, if they're D-wave, you sort of think that's a good possibility, even if they're P-wave. But that's another proof. And it's somewhat simpler than doing the Suey-Kirtley experiment. And one last, running over time, and we'll continue on next time, one last indication. I got asked this by Yvonne last time. What are some other ways to look for nodal behavior? Nodal being opening of a gap, something besides S-wave symmetry, is to look at the specific heat. We'll talk about this more next time, but it can look like this. If you plot the specific heat as a function of magnetic field in the superconducting state, where this shouldn't really be looking like this, you can get something that goes as the square root of h, and that's been predicted by Bulovic, and Catherine Moeller got a lot of mileage out of this early measurement in PRL, where gamma versus h. We've tried this ourselves. It's very hard to do, because again, you're looking at the C over the electronic term in the superconducting state, which is really pretty small, and you've got all these other contributions, especially when you put a magnetic field on. So Yeah, that's all for today. Thank you for your attention.